So in this video, we're going to look at exploring the behaviors of implicit relations. In other words, how do we take everything that we've done in this unit and apply it to implicit functions? So in analyzing implicit functions, the same ideas can be applied to implicit functions. So for example, where the critical point occurs when the derivative is 0 or undefined. The only difference is we need to consider both x and y values when we actually go into analyzing or calculating, finding those things. So for example, find the vertical tangent lines for the equation 3x squared plus 6x minus y squared plus 8y equals 16. So if we take the derivative of both sides, we're going to get 6x plus 6 minus 2y y prime plus 8y prime equals 0. So that means that we will get 8 minus 2y times y prime equals negative 6x minus 6. I'll just throw that over 1 since I drew that line in. Let's double check that. So that looks good. And then what we need to do here is solve for y prime. So y prime equals negative 6x minus 6 over 8 minus 2y. And they're asking for the vertical tangent line. So the vertical tangent line is going to be where the slope is infinity, or where it's undefined because it goes to infinity, which means we want where this is equal to 0, where the denominator is equal to 0. So y equals 4 is going to be the point that we want, but that's not a vertical line, right? A vertical line is an x value. So we're going to take y equals 4 and plug that back in up here and solve for our x values. So 3x squared plus 6x minus 4 squared plus 8 times 4 equals 16. So this will be, let's see, this bit right here will be 16, so when I add it, I'll get 32. 8 times 4 is 32, that'll end up canceling out. You can double check that. We get 3x squared plus 6x equals 0. And so that means we get 3 times 3x x plus 2 equals 0. So x equals 0 and x equals 2 are our vertical tangent lines. And again, we just did the same thing we did before. Find the derivative, set it equal to 0. Or sorry, find the derivative and then set it equal to 0 or undefined. In this case, we wanted undefined. So we get that vertical tangent. And that gave us 0 in the denominator and all of that as a result. For our second example, so let's cross that out and write example 2. Find the local extrema for x cubed plus xy equals negative 2. So we're going to use any of our tests to find these, but we'll start by taking the derivative. So that'll be 3x squared plus y plus xy prime equals 0. So y prime will equal 3x squared plus y divided by negative x, because I'll move the xy over and then divide it. Okay, great. So local extrema can occur where this equals 0 or it's undefined. So our critical points will be x equals 0 and also where the numerator equals 0. So that will be where 3x squared plus y equals 0. Now the problem with this is we don't know what, we don't know the x and y, but we do know that this original function tells us all of the places where, the relationships between x and y. So I'm going to solve this for y, and I'm going to get negative 2 minus x cubed over x is equal to y. So I can come back down here and plug it in. 3x squared plus negative 2 minus x cubed over x equals 0. So what can we do from here? Just making sure I didn't make any mistakes in that. Okay. So I'm going to multiply everything through by an x. So I get 3x cubed plus negative 2 plus negative x cubed equals 0. And that will give us that 2x cubed equals 2. So x cubed equals 1, so x equals 1. So these are our two critical points, x equals 0 and x equals 1. I should say critical points occur where x equals 0 and x equals 1. So what we now need to do is check what's happening to the slope at those points. So when x equals 0, we need to plug that in. So y prime of x equaling to 0 we're going to get 3 times 0 plus y over 0. That's not going to help us, is it? No. Because we said that's where the derivative is equal to 0. We need to do the second derivative test. So let's take the second derivative. That's why it wasn't working like I thought it should. The second derivative is going to be the derivative of the thing on top, which is going to be 6x plus y prime times the thing on bottom, negative x, minus the derivative of the bottom, which will be negative 1, times the top, which is 3x squared plus y, all over negative x. So y double prime is equal to 6x plus y prime, which will be 3x squared plus y over negative x times negative x minus negative 1, so plus 3x squared plus y all over negative x squared. The negative x and negative x can cancel. Y double prime is equal to 6x plus 6x squared plus 2y all over negative x squared. So plugging in 0 is not going to help us for that first critical point, other than telling us that if we look, that'll tell us it's a, tell us it is a inflection point, so we can know that this first one isn't a minimum or maximum. X equaling 1, plugging that in 1, 1. We need the y value, which will be up from the top up here. X equals 1 implies that y equals negative 2 minus 1, which would be negative 3 over 1. y equals -3. So coming down here, we've got y prime, double prime, is 6 plus 6 plus -6 over 1. So that's going to be positive. That means that this is concave up. So that puts us with a local min at 1, -3. So this is slightly more complicated than you'd generally be expected to do, just because there's a lot of math involved. But the idea I hope you can track, which is find the, let me mark this in yellow, find the first derivative, find the critical points where x equals 0, or where the derivative equals 0 or the derivative is undefined. And then, either use the first or second derivative test to evaluate and look for local minimum maximum. The only difference here is you will have to solve for the y value that goes with a given x value from time to time. So that's what we do with implicit relations.